The universe is 13.8 billion years old. For the first 380,000 years of its existence, it was too hot for atoms to form. For the next 100 million years, there were no stars. For billions of years after that, there were no planets, no oceans, no chemistry complex enough to produce anything capable of experiencing what was happening. And then, after 13.8 billion years of preparation, the universe produced something that had never existed before. Something that could look back at it. Something that could ask questions about it. Something that could measure it. And the moment that happened, according to one of the strangest ideas in modern physics, the universe may have needed it to start with the numbers, because the numbers are where this stops being philosophy and starts being a genuine scientific problem. The physical constants that govern reality are 25 numbers: the speed of light, the gravitational constant, the mass of an electron relative to a proton, the strength of the strong nuclear force, the cosmological constant, the value of the energy density of empty space. Each one is a precisely calibrated quantity that determines how the universe behaves at every scale, and every single one of them sits in an extraordinarily narrow range. Change any of them by a small fraction, and the universe produces nothing. No stars, no chemistry, no complexity, no observers. If the gravitational constant were slightly stronger, stars would burn out in thousands of years instead of billions. Not enough time for planets to form or life to develop. If it were slightly weaker, matter would never clump together enough to form stars at all. If the cosmological constant, the energy of empty space, were slightly larger, the universe would have expanded too fast for gravity to pull matter together into anything. It would be featureless, cold, and empty forever. The cosmological constant is the most extreme case. The value it has is approximately 10 to the power of 120 times smaller than quantum field theory predicts it should be. That is not a small discrepancy. That is the largest discrepancy between a theoretical prediction and an observed value in the history of physics. And if it were any larger by even a small amount, you would not exist, nothing would. In 1973, physicist Brandon Carter formalized the observation that had been nagging at cosmologists since the 1950s. He called it the anthropic principle. In its weak form, it says something almost tautological: we can only observe a universe compatible with our existence. Because if the universe weren't compatible with our existence, we wouldn't be here to observe anything. We are a selection effect. Our observation of a life-permitting universe doesn't tell us anything about whether life-permitting universes are common. It just tells us we're in one. But Carter's strong form says something more disturbing. It says the universe must be structured in such a way as to ensure the creation of observers within it at some stage. Not can produce observers. Must. The universe doesn't just happen to be fine-tuned for observers. The existence of observers is somehow a requirement of the universe's existence. Nobody has been able to fully explain what that means, or how it could be true, or whether it's true at all. Here is where John Archibald Wheeler comes in, and where physics starts doing something it very rarely does, reaching a conclusion it can't quite bring itself to state directly. Wheeler was one of the great theoretical physicists of the 20th century. He coined the terms black hole and wormhole. He worked with Bohr on nuclear fission, and in the 1970s, he spent years developing an idea he called the participatory universe, a vision of reality so radical that most physicists still don't know quite what to do with it. His starting point was the double-slit experiment. When a photon passes through two slits with no observer, it behaves like a wave, producing an interference pattern that shows it went through both slits simultaneously. When it is observed, it behaves like a particle, choosing one slit, producing no interference. The observer doesn't just record what the photon does. The observer determines what the photon does. Wheeler pushed this to its extreme with what he called the delayed choice experiment. In his setup, light from a distant quasar, billions of light years away, passes around a gravitational lens, giving it two possible paths. An experimenter can choose, after the light has already traveled for billions of years, whether to measure it as a particle or a wave. The choice made now, in the present, determines which kind of quantum history the photon had on its journey across the universe, a journey that ended billions of years before the Earth existed. His conclusion was stated simply and directly: no elementary phenomenon is a phenomenon until it is an observed phenomenon. And then he extended it. Beginning with the Big Bang, the universe expands and cools. After aeons of dynamic development, it gives rise to observership. acts of observer participancy via the mechanism of the delayed choice experiment, in turn give tangible reality to the universe, not only now but back to the beginning. Wheeler was arguing that observers don't just detect reality, they complete it. A quantum universe without observers is not a universe of definite facts. It is a universe of superpositions, of unresolved possibilities, of questions that have no answers. The observer is what converts possibility into actuality. And without observers, there may be nothing to convert. He crystallized this in 3 words: it from bit. Every physical thing, every particle, every field, every force, derives from information. From yes or no answers to physical questions. From observations. The universe is not made of matter that observers happen to notice. It is made of observations. It from bit. This leads directly to what Wheeler called the self-excited circuit. The universe produces observers. Observers, through quantum measurement, participate in giving the universe its definite properties, including, through the delayed choice mechanism, its past. The past of the universe is therefore not fully determined until observers exist to participate in determining it. The universe creates observers. Observers create the universe. The circuit is closed. The loop is complete. And nobody has been able to explain how it doesn't collapse into circular reasoning, or why it doesn't. In 2024, physicists Nemanja Kaloper and Alexander Westphal proposed something that had never been done before, a way to actually test the anthropic principle using astronomical observations. Their paper, focusing on cosmic inflation, dark matter, and axions, outlined specific conditions that upcoming observations could confirm or disprove. For the first time, the anthropic principle, previously criticized as untestable metaphysics, had a proposed experimental path. The results of those tests are not yet in, but the fact that they are being designed at all reflects how seriously the fine-tuning problem is being taken. This is not a fringe question. Physicist Bernard Carr, who co-authored the foundational 1979 paper on the anthropic principle with Martin Rees, described it in a 2024 interview as a stopgap, something physicists turn to when they cannot find a deeper physical explanation for why the constants have the values they do. If and when a final theory of physics arrives, Carr thinks it will predict the constants uniquely and render anthropic reasoning unnecessary. But that final theory has not arrived, and until it does, the numbers remain what they are. 25 constants, each one in a narrow range, all of them pointing, without exception, toward a universe that produces observers. There are 3 ways to live with this. The multiverse. If there are infinitely many universes with different values of the constants, then some will be life permitting, and only in those will observers exist to ask the question. No fine-tuning required, just selection. The design argument. The constants are what they are because something set them to produce observers. This is the theological interpretation that most physicists resist explicitly. And Wheeler's participatory universe. The constants are what they are because observers, through the act of quantum measurement, participate in constituting them. The universe fine-tunes itself retroactively through the existence of the observers it creates. All 3 remain live possibilities. None has been confirmed. None has been ruled out. What has been established is the thing that started this. The universe is 13.8 billion years old. It spent most of that time in conditions hostile to any form of complexity. It produced, after an extraordinary chain of physical coincidences, the specific conditions required for observers to exist. And the physics of quantum measurement suggests that observers don't just witness what happened during those 13.8 billion years. They participate in determining what happened. Wheeler put it this way: we are participants in bringing into being not only the near and here, but the far away and long ago. The universe kept creating observers, and physicists cannot explain why. But the most radical answer on the table is the one that refuses to separate the question from the questioner. The one that says the universe didn't create observers despite having no reason to. It created observers because, at some level of physics we haven't fully reached yet, it couldn't exist without them.